I'm very happy to introduce Juan Orendain, who will tell us how long does it take to frame a bicategory. Take it away.
All right, well, yeah, I'd like to start off by thanking Bryce and Tim for the invitation and just for organizing the workshop. Hopefully in the future, workshops and conferences in double categories become a normal thing. And yeah, I think this is a great starting point for that. So yeah, thank you very much. Yeah, so the title of the talk is How Long Does It Take to Frame a Bicategory? This is a long-term project that I've been working on and off for the past, I don't know, 4 years. And I'll be talking about a particular conjecture on this project of globularly generated double categories that I thought at some point in the summer of 2021 that I had solved positively, but it turned out I hadn't. So yeah, so I put it off for a while, and I'm just starting to think about it again with the help of one of my PhD students, Ruben Maldonado, who might be in the audience. So yeah, I'm going to talk about this conjecture, which is about the length of frame bicategories. So the plan for the talk, which might be a bit ambitious, is the following. So I'll first talk about mod-like bicategories. I'll say a few things about globularly generated double categories. I'll talk about length. Then I'll talk about free globularly generated double categories. Then about the canonical projection, and then I'll say a few things about frame bicategories and their length. Okay, so mod-like bicategories. So the prototypical mod-like bicategory is mod. So mod denotes the bicategory whose two cells are of this form, where A and B, the vertices, or the zero cells are unital complex algebras. The one cells M and N here are A, B bimodules, and the two cells, or the two cell phi here is a bimodule morphism from M to N. So a linear transformation from M to N satisfying this equation here for every A in A, B in B, and X in M. Horizontal identity and horizontal composition in mod are provided by the trivial bimodule associated to an algebraic construction and the relative tensor product construction. If A and B are algebras, then A and B are isomorphic or weakly isomorphic in mod if and only if A and B are monoidal equivalent, and a one cell M is adjoint if and only if as a bimodule is finitely generated and projected. So this bicategory mod contains some very nice information about the general theory of representations of complex unital algebras. But this is just one part of the story. We have a double category of algebras, bracketed mod. So bracketed mod denotes a double category whose squares or two cells are of this form, where again A, B, C, and D are complex unital algebras. M and N, the horizontal edges, are A, B, and C bimodules respectively, where now we have this vertical arrows, F and G, which are unital morphisms from A to C and from B to D respectively. And now two cells or squares are again linear transformations from N to N, but that satisfy this sort of equivariant bimodule condition. So the squares in bracketed mod are equivariant bimodule morphisms. Yeah, horizontal identity and horizontal composition in bracketed mod are defined by the obvious functorial extensions of the function associating to every algebra its trivial bimodule and the function associating to every compatible pair of bimodules its relative tensor product. So these two functions have obvious functorial extensions, and well, these make bracketed mod into a double category. Oh, sorry, there's a typo here. So what is the relation between bracketed mod and mod? It turns out that bracketed mod, the horizontal bicategory of bracketed mod, is the bicategory mod. So
this H bracketed mod means that we just consider the globular squares of the double category bracketed mod. So the squares as above here, where the vertical arrows are identities. And so that becomes a bicategory, and we can identify the bicategory mod with that bicategory. So what we should read from this equation is that this bicategory that we started with, and that is well known, is sort of the shadow of this larger structure, the bracketed mod double category. And this is sort of a theme that happens or repeats itself quite a lot. So what can we get from this equation, from the fact that the horizontal bicategory of bracketed mod is the usual bicategory mod? There's one very important thing that we can get out of this thing. Tensor products of algebras by modules and by module morphisms provide this bicategory mod with the structure of a symmetric monoidal bicategory. Now, if you've seen the definition of a symmetric monoidal bicategory, it's this sort of intimidating set of axioms, sometimes very well organized, sometimes not so much. I like the way Mike Stay presents the axioms in his paper on compact closed bicategories. So if you've never seen the axioms for a symmetric monoidal bicategory, I strongly recommend looking at that paper. But yeah, in the end, the point is that in a symmetric monoidal bicategory, the coherence data comes in the form of one cells, which in this case would be bimodules, which should be invertible, and that should satisfy a bunch of very complicated equations. But coherence data for the tensor product of algebras is actually naturally defined in terms of unital morphisms, not in terms of bimodules, and it satisfies the Maclane equation strictly. So it just seems like the definition of a symmetric monoidal bicategory is a bit too much for what we want here. And so we would need a different language to express the fact that mod is a symmetric monoidal bicategory a bit more efficiently. And so, well, tensor product and vertices, edges, and squares in bracketed mod provide bracketed mod with a structure of symmetric monoidal double category, where by that I mean this makes bracketed mod into a weak monoid in the 2 category of double categories. And moreover, bracketed mod is a frame bicategory, which I'll talk about a bit more later. But the point of this is that the coherence isomorphisms for bracketed mod descend to coherence isomorphisms for a symmetric monoidal structure and mod, with the tensor product being the horizontalization of the tensor product of bracketed mod. So this general procedure of doing this was proven or provided by Schulman in a classic paper. So I'm being very imprecise with this here, but the point is that bracketed mod is sort of the correct framework to equip the bicategory of algebras with a 2-dimensional symmetric monoidal structure. Yeah, so this story is sort of, it works out pretty well. So you want your bicategory of bimodules or algebras to become a symmetric monoidal bicategory. The language of symmetric monoidal bicategories is a little bit too unnatural or complicated for that, but you can extend your bicategory to a frame bicategory, and then a symmetric monoidal structure is pretty natural there. And then you can just flatten that into a symmetric monoidal structure on your original bicategory. So you can sort of bypass the Kaprano, Vygotsky, etc. axioms for symmetric monoidal bicategory. Now, Mike Schulman, in his paper on constructing symmetric monoidal bicategories, has an observation which says that there are essentially 2 types of bicategories. Well, I don't think this, well, I'm not sure if he says it like this, but if he did, I don't think this would be as much like this anymore. But there's not 2 types of bicategories, but there's 2 large classes of bicategories exemplified by cat and mod, where a cat has objects and some sort of functions between objects, functors, as 1 cells, and morphisms between these 2 functions as 2 morphisms. So these are natural transformations. And mod is a bit different. Mod has objects as 0 cells as objects, and other types of objects, parameterized objects as 1 cells, and functions between 1-dimensional objects as 2 morphisms. So in this case of bicategories of objects, parameterized objects, and morphisms between objects, there is usually a correct or natural notion of morphisms between objects. In mod, sorry, there's a typo again here. So in mod, for example, you have your objects or algebras, your parameterized objects are bimodules, and the morphisms between these parameterized objects are bimodule morphisms, and your correct notion of morphism between zero-dimensional objects is unital algebra morphisms. So the bicategories fitting this description are referred to as mod-like bicategories. So these are bicategories whose objects are algebras of some sort. The bicategories whose objects are algebras of some sort. One morphisms are bimodules over this algebras, and two morphisms are bimodule morphisms are mod-like. So the slogan for mod-like bicategories is that a mod-like bicategory B should have a category of function or correct morphisms B star that is not directly included in the bicategory. There should be a clear lift of B to a double category C, having this correct notion of morphism encoded in the category of objects, and such that the horizontal bicategory of this extension should be the original bicategory. So a natural symmetric and a natural symmetric monoidal structure on the mod-like bicategory should be better expressed as a symmetric monoidal structure on the double category, extending it. So yeah, so the idea is that if you have some sort of a bicategory of algebras, bimodules, and bimodule morphisms, then yeah, again, you should have a correct notion of morphism between your sort of algebra objects, and you should be able to encode your bicategory together with this correct notion of morphism into a double category and make that into a symmetric monoidal double category in such a way that that makes your bicategory into your symmetric monoidal into a symmetric monoidal bicategory. Now, if we apply this program to different notions of algebras, then well, that sometimes work and sometimes it doesn't work. So for example, I got interested in this project by studying binomial algebras, and well, I was studying conformal field theories and so binomial algebras, and yeah, binomial algebras. Well, I don't want to bore you with the definition of what a binomial algebra is, but a binomial algebra is a type of topological algebra used in conformal field theory, low dimensional topology, and other areas. They're usually referred to as non-commutative measure spaces. There's a natural notion of bimodule for binomial algebras. There's also a natural notion of bimodule morphism. We call this intertwiners. There's a relative tensor product, which we call the confusion tensor product, or CFTP. And there's a relative tensor unit, which we call the Hargreaves standard form. So these are a lot of words, but the point is that there's this sort of structure, binomial algebras. These are algebras of some sort. These algebras have bimodules. These bimodules have morphisms. We have a relative tensor product, and we have a relative tensor unit. And so binomial algebras, bimodules, and intertwiners form a bicategory, which we call W star, where horizontal composition is this relative tensor product, and where horizontal identity is our tensor unit, relative tensor unit. So this is obviously a mod-like bicategory. So this bicategory has algebras of some sort as objects, bimodules as one cells, and morphisms between bimodules as two cells. Now there is a tensor product for binomial algebras, bimodules, and intertwiners, and that should make W star into a symmetric monoidal bicategory. So the tensor product is the usual completed tensor product of binomial algebras, Hilbert spaces, and so on. But yeah, that should naturally make this bicategory into symmetric monoidal bicategory. Now, again, we're in sort of the same situation as before. The coherence data for W star is actually defined in terms of morphisms of binomial algebras, not in terms of Hilbert bimodules. And so if we want to make W star into a symmetric monoidal bicategory, then we should lift W star into a double category, actually into a frame bicategory, bracketed W star of equivariant bimodule morphisms. Also, I didn't write it here, but there's a natural notion of morphism of the Neumann algebras, which is called normal morphism. Yeah, so this problem has already been considered by Bartels, Douglas, and Henriquez in 2014 in a paper called Index and Dualizability of Factors, I believe. And so they try to define a frame bicategory of a Neumann algebras by modules and equivariant intertwiners with respect to general normal morphisms. But they ran into a couple of problems. So the main one was that there was no analytic tools to define a functorial horizontal identity nor a functorial confusion tensor product on general normal morphisms. So what they did was to define a double category of Neumann algebras where the vertical arrows were not all the natural morphisms between Neumann algebras, but just morphisms where they could define their extensions. So they restricted themselves to simple Neumann algebras, which we call factors, and sort of finite morphisms between them, which we call, morphisms of finite Jones index. So these are sort of special morphisms that have very nice properties. And so restricting themselves to factors and finite index morphisms, they could get a double category of these Neumann algebras of factors and finite index morphisms. So they got a double category, which I call BDH. So by Bartels, because of, their names, Bartels, Douglas, and Henriquez. So, okay, they have this double category BDH, but can we get a general double categories, a general double category of general Neumann algebras or just factors and general morphisms, not necessarily finite Jones index morphisms between them? Well, the problem is that the theory of Neumann algebras does not give us direct tools to extend BDH to a general morphisms. And there's no applicable general lifting techniques available. So if we have a bicategory and a collection of morphisms, a category of morphisms, then we don't have general techniques to lift that into a double category, having our original bicategory as horizontal bicategory and our given collection of morphisms as collection of vertical arrows. Now, the strategy that I tried to follow when trying to think about this problem was to solve the problem by understanding any extension. I mean, I wanted an extension of BDH, specific extension of BDH. I wanted a double category of Neumann algebras, bimodules, general or factors bimodules, and equivariant intertwiners with respect to general morphisms between factors. But there was a question of, are there any other categories of factors or Neumann algebras? And if so, I could try to understand this double category that I was looking for in terms of its surrounding categorical structure, that is in terms of its position in the category of general double categories of Neumann algebras. So yeah, we have this drawing here. So this is supposed to denote the category of double categories of Neumann algebras. So this wouldn't be in general, or this, I'm sure this wouldn't be compact closed or anything, or rigid as this drawing suggests, but yeah, whatever. This is a very nice drawing. So yeah, we would have this, and then the question mark would be the double category of factors that I'm looking for. And so I want to know what surrounds it in this double category, and in terms of that, sort of guess what this double category would look like. So the obvious question was, are there any double categories of factors at all? So is this sort of gray shaded region or gray shaded square non-empty? So yeah, that was the first question. Are there double categories of factors or Neumann algebras at all? Or in general, given a bicategory and a category of morphisms, are there double categories? Are there always double categories extending the bicategory and the category of morphisms? And yeah, so I just started by putting this in sort of formal terms. So that's where decorated bicategories came in. So a decorated bicategory is a pair B star comma B, where B star is a category and B is a bicategory such that the objects of B star and the objects of B are the same. So we represent a decorated bicategory as a bunch of diagrams of this form. So the globular diagrams represent the bicategory B, and the vertical arrows represent the category B star. So we're assuming that the vertices of the two diagrams are the same. So an example of this is, of course, if C is a double category, then the pair formed by the category of objects C0 of C and the bicategory, the horizontal bicategory HC of C is a decorated bicategory. So the category of objects of C0 and the category of 0 cells of HC are the collections, the objects of C0 and the objects of HC are the same, or the objects of the double category C. So yeah, if C is a double category, then this is a decorated bicategory, and we write this as H star C, and we call it the decorated horizontalization or the decorated horizontal bicategory of C. So what we're thinking about is the following problem. So given a decorated bicategory B star comma B, we want to find double category C such that H star C, the decorated horizontalization of C, is the decorated bicategory that we started with, B star comma B. So we call any such double category C an internalization of B star comma B. And well, once we've found internalizations for our decorated bicategory, can we understand other internalizations of B star comma B? Can we understand the structure of the collection of internalizations of a given decorated bicategory B star comma B? So we call this the problem of existence of internalizations. So the problem of existence of internalizations asks if the decorated horizontalization construction is generic. So is every decorated bicategory the decorated horizontalization of a double category? So we can think of this problem of existence of internalizations as a problem of coherently filling hollow squares of this form here. So we start with a decorated bicategory B star comma B, and with the one-dimensional data of B star comma B, we can form hollow squares like this. So we have objects, we have vertical arrows, and we have horizontal or one cells, horizontal arrows or one cells given to us by B. And so we're asking if we can fill these hollow squares in such a way that we get a double category, and the vertical arrows and the globular squares are fixed. The vertical arrows are the arrows of B star, and the globular squares are the two cells provided to us by B. So problems of filling squares with globular data appear in a lot of places, but classically in Ronnie Brown's proof of the two-dimensional Seifert-van Kampen theorem, and also in the definition of frame bicategory by Mike Schulman, and in some other places, I guess. Yeah, so, okay, so we're interested in this problem of internalizing a decorated bicategory. Now we want to solve that minimally somehow. So suppose C is a double category. If we write gamma C for the minimal subdouble category of C containing every horizontal identity square and every globular square of C, then we have the following lemma. So if C is a double category, then the decorated horizontalization of C equals the decorated horizontalization of this gamma C. And if D is any subdouble category of C satisfying the equation, this equation here, so having the same decorated horizontalization as C, then gamma C is a subdouble category of D. So what this says is that if C is a double category, then C is of course a solution to the problem of existence of internalizations for its decorated horizontalization. One says that, well, that's, yeah, but gamma C is also a solution to that problem contained in C. And 2, gamma C is the minimal solution to that problem within the double category C. So we call gamma C the globularly generated piece of C. Okay, if C is a double category, then the globularly generated piece gamma C of C is a sub-double category of C, having the same decorated horizontalization as C, and being minimal with respect to that property. So, well, in general, we call a double category C globularly generated if any of the following 3 equivalent conditions is satisfied. So first, the globularly generated piece of C, gamma C, is equal to C. C is generated as a double category by its globular squares. Or 3, if C contains no proper sub-double category C with the same decorated horizontalization as C. So yeah, so number 2 says that C is double category C is globularly generated if every square in C admits a subdivision, I don't know, like this, where every smaller square is either a horizontal identity or a globular square. And number 2 says that, number 3 says that a double category C is globularly generated if it's minimal with respect to being a solution to the problem of existence of internalizations of its decorated decorated internalizations or decorated horizontalization. So yeah, globularly generated double categories, if you're interested in this problem of existence of internalizations, yeah, are good. They're just minimal solutions to that. And they seem to have nice structure. Now, gamma square of C equals gamma C for any double category C. And so gamma C, the globularly generated piece of any double category C, is globularly generated. So the globularly generated piece of a double category C is not just the minimal solution to the problem of existence of internalizations of its decorated horizontalization, but it's also the maximal globularly generated sub-double category of the double category C. Yeah, so this can be written categorically in nice terms. So we write GCAT for the sub-2 category of double categories generated by globularly generated double categories. We write BCAT star for the category of decorated by categories, decorated pseudofunctors. Then the function associating to every double category C, its globularly generated piece gamma C extends to a functor gamma from double categories to globularly generated double categories. We can prove that gamma is actually a 2 coreflector and so it's one-dimensional piece. It's a fibration. And so double categories, the category of double categories is actually indexed by globularly generated double categories. And not just that, but the function associating to every double category C, its decorated horizontalization also extends to a functor from double categories to decorated by categories. And so the following triangle here commutes. So the decorated horizontalization functor breaks into this fibration gamma into globularly generated double categories and the restriction of H star to globularly generated double categories. And H star is constant. So H star is constant along this, the fibers along the gamma functor. So the lesson here is that if you're interested in internalizations and you don't know how to solve internalization for a given decorated by category, then you first study basis for this globularly generated piece functor gamma. So we study globularly generated double categories, internalizing your decorated by category that you might be interested in. Yeah. So, okay, well, so what about this gamma functor or this gamma construction? So we have the following lemma, so we can actually compute this in several examples. So we have the following lemma: if C is a double category and phi is a square in C, then if phi is not globular, but it is globularly generated, then the left frame and the right frame of phi are equal. So the left and right edges of phi are equal. So that says that every non-globular, globularly generated square in a double category C is a horizontal endomorphism. So if we want to compute explicitly the globularly generated piece of a double category, well, we already know so if our double category is C, then we know the objects, the vertical morphisms, the one cells, and the globular morphisms of that globularly generated double category. So we would only need to compute the squares that are in the globularly generated piece that are not globular, and these are horizontal endomorphisms. So we just need to determine which horizontal endomorphisms of a given double category are in the globularly generated piece. So, okay, using that, we compute the globularly generated piece of bracketed mod. So we know objects, horizontal and vertical morphisms, and globular squares of gamma bracketed mod. So we just need to compute the non-globular, globularly generated horizontal endomorphisms. And so this just turns out to be some sort of a condition. So if R and S are algebras, then an equivariant morphism of this form, so F phi F, so a horizontal endomorphism from M to N, where M is an R bimodule and M is an S bimodule, is a square in bracketed mod. Then F phi F is, we say that that is two subcyclic if there exist submodules L and K of N, such that L as an R bimodule, by pulling back the structure of S bimodule by F, is R cyclic, and K as an S bimodule is cyclic, and the image of phi is contained in L. So, well, just some sort of a condition. So an example here is R and S rings have a morphism from R to S. The horizontal identity is two subcyclic. Now we have the following lemma: the non-globular squares of gamma bracketed mod are precisely the two subcyclic squares. So yeah, we just gave conditions to characterize the non-globular horizontal endomorphism squares that are in the globularly generated piece of bracketed square. So yeah, we can say what bracketed square, gamma bracketed mod, the squares, the globularly generated squares of bracketed mod are. So, okay, well, what can we say about globularly generated double categories? So suppose C is a globularly generated double category, then the category of squares of C has a very nice canonical filtration, which is defined as follows. We define this filtration inductively. So we first write H0 for the set of globular and horizontal identity squares of C. Then we write V1 for the category generated by H0, the subcategory generated by H0 in the category of squares of C with vertical composition. Now, suppose Vn minus 1 has been defined for some n, then we define Hn as the sub-pseudo category of the category of squares of C under vertical composition generated by Vn minus 1. Oh, sorry. So Hn is the sub-pseudo category of the category of squares of C under horizontal composition generated by Vn minus 1, and then make Vn to be the subcategory of C under vertical composition generated by Hn. So we have the following. So for every n, Vn is contained in Vn minus 1, and that is obviously contained in the category of squares of C. And the limit, or the union of the Vn's, is the category of squares of C. So the chain formed by the categories Vn is a filtration for the category of squares of C under vertical composition. So we call this filtration the vertical filtration of C. So globularly generated double categories, their categories of squares come equipped with a canonical filtration, which we call the vertical filtration of the double category. So we can see this filtration geometrically in a very nice way. So suppose C is a globularly generated double category. So we think of globular and horizontal identity squares as squares of complexity 0. So we're taking the point of view that if we have a globularly generated double category, then we know everything we need to know about its decorated horizontalization. So we know everything we need to know about its globular squares and its horizontal identities. So we think of those squares as being of complexity 0, the easiest possible squares. So we draw them as squares marked with a 0. So the category, the set H0 is a collection of squares of complexity 0. Then V1 is a collection of squares that can be subdivided as a vertical composition of squares of complexity 0. So geometrically, V1 is the collection or the category of squares that can be subdivided like this. So it can be written as a vertical stack of squares marked with a 0. So we say that these squares are of complexity less than or equal to 1, and we draw them as squares marked with a 1. So given two compatible, horizontally compatible squares phi m psi and V1, so it might be the case that we can find compatible complexity less than or equal to 1 presentations of phi m psi. That is, it might be the case that the horizontal composition of phi m psi can be made to look like this. So we subdivide phi m psi into squares marked with a 0, and it might be the case that those subdivisions match horizontally in the sense that we can compose each of the squares subdividing phi m psi horizontally. And so in that case, observe that the horizontal composition of squares of complexity 0 is of complexity 0. And so we would get a subdivision of the horizontal composition of phi m psi into a vertical composition of squares of complexity 0. And so the horizontal composition would be of complexity less than or equal to 1. But that doesn't happen in general. So the horizontal composition of phi m psi can look like this for any complexity less than or equal to 1 decomposition of phi m psi. So in that case, we say that the horizontal composition of phi m psi's complexity is of complexity less than or equal to 1 plus 1/2. And H1, so we started with H0, we got V1, and then H1 is the pseudo category of squares of complexity less than or equal to 1 plus 1/2. Now, yeah, we can do this inductively. And so if we assume that we have defined squares of complexity less than or equal to n minus 1, then square of complexity less than or equal to n minus 1/2 are now squares that can be subdivided as horizontal compositions of squares of length, of complexity less than or equal to n minus 1. So geometrically, these are squares that can be drawn like this, where the ii's or ij's are less than or equal to n minus 1. So hn minus 1 is a pseudo category of squares of complexity less than or equal to n minus 1/2. And so now we can define Vn as the subcategory of the category of squares of C, of squares that can be subdivided like this, where the ij's are less than or equal to n minus 1/2, or just as the subcategory of the category of squares of C were generated by squares as above. Yeah, so this Vn's form a filtration. The fact that the Vn's form a filtration just means that every square in C has some complexity. Okay, so with this, we can define the length of a double category. So if C is a globularly generated double category and phi is a square in C, then we define the length of phi, L of phi, as the minimum n such that phi is in the category Vn. So L of phi is the minimum n such that phi is of complexity less than or equal to n. So L of phi we call the vertical length of phi. Now we can define the length of a double category C, LC, as the supremum of all the lengths of squares in C. So of a globularly generated double category C, we call LC the vertical length of C. And if C is just a general double category, not necessarily globularly generated, then we define the vertical length of C, LC, as the length of the globularly generated piece of C. Now, the intuition behind this number, the length of a double category, is that it measures the complexity of mixed compositions of horizontal identity and globular squares of C. So for example, if a double category C has length 1, or a double category C has length 1 if and only if every square in gamma C can be written as a vertical composition of globular and horizontal identity squares. That is, every globularly generated square can be written like this. And any two horizontal compatible expressions just match as before. So examples of double categories of length 1 are, for example, the vertically trivial double category associated to a 2 category has length 1. The double category of quintets of a 2 category again has length 1. Bracketed mod has length 1. BDH has length 1, and many other double categories that we know have length 1. So the question is this length invariant trivial? Okay, well, to solve this this question, we need just a way of constructing globularly generated double categories apart from taking the globularly generated piece of a already existing double category. So, okay, so this is the free globularly generated double category construction. So suppose B star comma B is a decorated bicategory. So we wish to associate to B star comma B a globularly generated double category defined only through the data of B star comma B. So the idea is the following. So we start with B star comma B, and we formally reconstruct a vertical filtration with the data of B star comma B, and then turn that into a globularly generated double category. So we start with diagrams like this, vertical arrows and globular 2 cells, and then we just puff this up into squares. So the vertical arrows, we puff them up into horizontal identity squares, or squares, formal squares that look like horizontal identities. And we puff up the globular diagrams into squares that are globular, or that look like globular diagrams. Oh. So we stack the above diagrams vertically, then horizontally, then again vertically, and so on and so forth. And we get a bunch of formal squares that can be subdivided into this formal horizontal identities and formal globular diagrams. Where, yeah, the smaller squares in this subdivision here are in the formal shape that we defined before. So now once we've done this, we carefully choose an equivalence relation R in the set of this formal squares containing both the exchange relation and the composition information of B star comma B. And then we just consider the quotient and call that Q B star comma B. So yeah, theorem proven in 2019 says that if B star comma B is a decorated bicategory, then Q B star comma B is actually a globularly generated double category, having the same category of objects as the decoration of B star comma B, and containing the bicategory, so such that the horizontal bicategory of Q B star comma B contains the original bicategory. We call Q B star comma B the free globularly generated double category associated to the decorated bicategory B star comma B. But there is one thing that, yeah, it's important. The equality, so the equation H star Q B star comma B equals B star comma B does not always hold. So the free globularly generated double category of a decorated bicategory is not necessarily an internalization of the decorated bicategory. But if that happens, then we say that the decorated bicategory B star comma B is saturated. And we have sort of easy tests to define if a decorated bicategory is saturated. So for example, if B star has no sections or retractions, that is, if B star comma B is reduced, then in particular, if B star is the looping category of a reduced monoid, then B star comma B is saturated. And so it's free globularly generated double category internalizes it. And so we have the following lemma. If B star comma B is a decorated bicategory, then the free globularly generated double category associated to the decorated horizontalization of the free globularly generated bicategory of B star comma B is actually the free globularly generated double category of B star comma B. And so the decorated horizontalization of the free globularly generated double category of a decorated bicategory B star comma B is saturated. So the thing that we can get from this is that if B star comma B is not saturated, then we can always enlarge B star comma B canonically in order to obtain a saturated decorated bicategory. In the same paper in 2019, we proved that the decorated bicategory of factors, which is the thing that started this whole program, was saturated. And so we were able to construct a double category of factors, the free globularly generated double category associated to the decorated bicategory of factors by modules and intertwiners decorated by general morphisms of Riemann algebras, which was pretty good. So, okay, one other thing that we could use this free globularly generated double category construction on was to provide examples of globularly generated double categories of non-trivial length. So as I mentioned before, there were a bunch of examples of globularly generated double categories of length 1, but we could construct globularly generated double categories of arbitrary length with this technology. So an example is the following. So consider the bicategory B having 3 objects A, B, and C, and only one non-trivial two-cell. So sorry, trivial where all the 1 cells are trivial. So red 1 cells are supposed to be identity 1 cells, and one non-identity 2-cell in B. So yeah, like this. And they're created B by the category B star generated by this diagram here. So here, so this is not what written, but so I'm assuming that the composition of the orange arrow and the green arrow is equal to the composition of the orange arrow and the yellow arrow, and that's the purple arrow. So if we do that, then we can construct this 2 composite squares. We just have A, B, and C. And then we consider this squares here, where the top and bottom squares and the 2 composite squares are horizontal identities. And observe here that the left and right frame of both squares is the purple arrow. So this can be composed. But this 2 squares cannot be subdivided into squares of complexity 0 that match. So the horizontal composition of these 2 squares is of length 2, and thus the length of the free globularly generated double category of this decorated bicategory is greater than or equal to 2. And we can actually extend this construction to prove that there exists double categories of length n for every n, and we just take the limit of those and we construct a double category of length infinity. So length is definitely not trivial. Okay, now another thing that we can say is this canonical projection. So we prove the following theorem. So if B star comma B is a decorated bicategory and C is an internalization of B star comma B, then there exists a double functor pi C, a unique double functor pi C from the free globularly generated double category Q B star comma B associated to B star comma B to this internalization C. C has to be globularly generated. I'm sorry, I didn't write that here. So if C is a globularly generated internalization of B star comma B, then there exists a unique double functor pi C from Q B star comma B to C, such that pi C restricted to B star comma B is the identity of B star comma B, and pi C is surjective from globular squares of C. We call this pi C the canonical double projection of C, and the function associating to so observe that the function associating to every decorated bicategory B star comma B, it's free globularly generated double category Q B star comma B extends to a functor Q from the category of decorated bicategories B cat star to the category of globularly generated double categories G cat. And we could prove that this functor was left adjoint to decorated horizontalization, where the P pi C's form a co-unit for this adjointion. So Q, we think of Q as this decorated version of the quintet's construction. Moreover, the decorated horizontalization functor restricted to globularly generated double categories is actually faithful, and so restricted to globularly generated double categories, this free globularly generated double category construction is a free construction. Now, suppose B star comma B is a decorated bicategory, then with this free globularly generated double category construction, we can define a length or a number for B star comma B itself. So we define the length of B star comma B to be the length of the free globularly generated double category associated to B star comma B, and that depends only on B star comma B. Now, if C is an internalization of B star comma B, then the length of C is less than or equal to the length of B star comma B. And so that's just the existence of the canonical double projection and the fact that that length behaves well with respect to surjective double functors. So we can always, if we start with a decorated bicategory B star comma B, and if we're able to compute its free globularly generated double category and we're able to compute the length of that, then we can always bound the length of every other globularly generated internalization of the decorated bicategory by that length, which is pretty cool. So actually, with this construction, with the canonical double projection, we were able to construct a new double category of factors. So we started with the decorated bicategory of factors, then we proved that that was saturated. So the free globularly generated double category of that was an internalization. But we just defined a canonical double projection satisfying some relations in such a way that we got a new double category of factors that actually extended BDH. And so we were able to extend BDH to a double category. And not just that, we were able to define two non-equivalent double categories of factors. And we just wanted one, which was good. And these both double categories are of length 1. Okay, now frame bicategories. So most of the audience, I'm sure, knows about them. And already in some talks, some people talked about this. But yeah, so a frame bicategory is a double category C such that any of the following 3 equivalent conditions are satisfied. So first, the left times right frame. So the functor associating to the category of squares, to every square, its left arrow times its right arrow. That's a fibration. Equivalently, that's an up fibration. And 3, every vertical edge has a companion and a conjoint. So an example of a frame bicategory is bracketed mod, the double category of morphisms, the fundamental double groupoid of a three filtered topological space, the double category of adjoint pairs, the double category of structured cospans on a category C, the double category of polynomial functors, the double category of polynomial comonoids, BDH, etc. So we have a bunch of examples, interesting examples of frame bicategories. Now, what's cool about frame bicategories is the following. So if C is a frame bicategory, then again, L times R is a fibration, which means that for every empty lower frame, shell, or boundary, or whatever that we can form in our double category like this. So if we have objects A, B, C, and D, a vertical edges F and G, and a horizontal edge M, then we can fill that into a square that is Cartesian with respect to L times R, which means that if we have a square like this, where the vertical edges are composite, then we can always write that as a composite square like this, just a general square on H and K, and composed by our Cartesian square on F and G. So in particular, for any square like this, phi, we can consider this factorization here, and then we can write our original square phi here as a composite of a globular square and a Cartesian square, which is pretty nice. So we're interested in, again, double categories, globularly generated double categories. So double categories where every square can be written as some sort of composition of globular squares and special squares, horizontal identity squares, not necessarily Cartesian, or definitely not Cartesian, but this sort of suggests that there should be something we could do with frame bicategories and globularly generated double categories. Now, the thing about frame bicategories is that they organize into a subtope category, into 2 category, BCAT FR. So an asymmetric monoidal frame bicategory, as always, is a commutative pseudomonoid in BCAT FR. An asymmetric monoidal structure on C0 and C1 plus, so a symmetric monoidal structure on a frame bicategory is just a symmetric monoidal structure on the category of objects of C and the category of squares in C plus some pair of EC compatibility conditions. So a frame double category is something that is sort of easy to define, something that's almost 2 one-dimensional things, which is, good. So we have the following theorem. So if C is a symmetric monoidal bicategory, then every choice of cleavage for the fibration L times R defines a symmetric monoidal structure on the horizontalization of C. So this is Schulman. And so we have the following observation. So this was the motivation for this project. So we wanted to define symmetric monoidal structures on this bicategory of binomial algebras. Again, we want to extend that to a double category, but not just that, to a frame bicategory. We want to define a symmetric monoidal structure on that frame bicategory such that the horizontalization of that is a symmetric monoidal structure on our bicategory of binomial algebras. Now, we know how to extend this bicategory of binomial algebras, or at least factors, to a double category in 2 ways at least, but we don't know if we can extend that to a framed bicategory. Now, of course, so we're interested in the following problem. So if we can extend a decorated bicategory into a double category, if we can internalize that, how can we decide if we can internalize that into a frame bicategory? Now, one thing is that globularly generated frame bicategories are all vertically trivial. So we can't have globularly generated bicategories that are globularly generated double categories without them being trivial. This is just the fact that there's no non-trivial companions and conjoints. So every squared is either globular or horizontal endomorphism in a globularly generated double category, which is okay. Well, so globularly generated double categories are, unless they're trivial, not frame bicategories, but we might have a globularly generated double category, and in its gamma fiber, we might have a frame bicategory. Does that always happen? That was one question. So there exists globularly generated double category C, such that there doesn't exist a frame bicategory D in its gamma fiber. So there exists some globularly generated double categories without frame bicategories in their fiber. Okay, well, that's not good. Or, I mean, it's expected, but I don't know. Now we have the following question. What can we say about globularly generated double categories having frame bicategories in their gamma fiber? Well, we have one way of distinguishing globularly generated double categories, that is through the length. So that question translates in terms of length. What is the length of a frame bicategory, which was the title of the talk? And the conjecture is that that is 1. And the support is that we have some computations on frame bicategories, and that's always 1 for some reason, but we can't really prove this formally, and we're working with that on that. So yeah, these are some references, and yeah, that's it. Thank you.
Okay, thank you for your talk.
Yeah, thanks.
We have enough time for maybe 1 or 2 questions. If anyone has a question, feel free to jump in.
Can you maybe just show the references instead of this slide, please?
Oh, sorry. Just go here.
Yeah, thank you.
So just a very basic question. I mean, you're working with these decorated bicategories and you're constructing these globally generated double categories from them. What if your decorated bicategory is a pair of a category and just another category instead of a bicategory? Do you get something like really trivial, or is it still interesting?
Yeah, it's trivial to find. I believe it's trivial to find an internalization. So a double category. It's not too difficult to do that. But then, yeah, well, I'm not sure. In some cases, it is pretty trivial. But so in general, I'm not sure. But also, yeah.
Is the double category of squares globally generated?
No. So the globally generated piece of the category of squares and also of the double category of commuting squares, that's always trivial.
Right, okay.
So it's just horizontal, so it's the double category generated by horizontal identity squares and vertical identity squares. Okay. But there's some really interesting examples. So for example, the one example that I have of a double category that cannot be, that a globularly generated double category that does not have a frame bicategory in its fiber, in its gamma fiber, is a double category that of commuting squares that actually Direct asked about about a year ago, and that was really interesting. So they can be very interesting objects still in this context.
Okay, thank you.
Yeah.
It looks like we're out of time, so let's thank our speaker again for an excellent talk.